Starting with this circle, we will pick a point at random outside the circle and call it D, and we will draw a line from D to the circumference of the circle. Now watch as I rotate this point around the circumference of the circle. Sometimes this line is intersecting the circle, and sometimes it is not. When this line is intersecting the circle, we call that portion of the circle the concave part. When the line is not intersecting the circle, we call that the convex part. Now let's move the point such that the line is tangent to the circle. And we'll move this point along the concave part of the circle so that the line intersects the circle. And let's also label the center of the circle and call it M. Notice as I rotate this point along the concave circumference of the circle, the line gets longer and longer until we intersect M, and then the line gets shorter and shorter again. This is the first part of the proposition that we will prove. Moving the point such that the line is tangent to the circle again, we will instead move the point through the convex part of the circumference. Notice that the line starts out long and gets shorter and shorter until the line is collinear with the center of the circle. And then, continuing the rotation, the line gets longer and longer until we are tangent again. This is the second part of the proposition we wish to prove. The third part of the proposition that we wish to prove is that, given a point on the circumference, the line connecting that point and D has only one other point on the circle, such that the line from D to that point will be equal to the first line. Let's prove the first part of the proposition. Let's draw DA that goes through the center M, and DE, and DF, and DC. What we want to show is that DA is greater than DE, which is greater than DF, which is greater than DC. First, connect ME, MF, and MC. This gives us three triangles. A property of triangles is that any two sides, together, will be longer than the third. Another property to take note of is that MA, ME, MF, and MC are equal lengths because they are radii of the same circle. Let's first prove that DA is greater than DE. Since DEM is a triangle, ME plus MD are greater than DE. But ME is equal to MA, so AM plus MD, which is AD, is greater than DE. Let's now prove that DE is greater than DF. Noticing that we have two triangles where FM is equal to EM, and they both share MD, notice that angle FED is less than angle EMD. So we know that FD will be shorter than ED, corresponding to a smaller angle. Similarly, CD will be less than FD. This proves the first part of the proposition. Let's now prove the second part. We will draw DG such that DG is collinear with M, the center of the circle. And we will also draw DK, DL, and DH. What we are trying to prove is that DJ is less than DK, which is less than DL, which is less than DH. The first thing we will do is draw MG, MK, ML, and MH. This gives us three triangles. A property of triangles is once again that two sides taken together are greater than the third. Note also that MH, ML, MK and MG are equal because they are radii of the same circle. Let's first prove that DG is less than DK. Now we know that MD is less than MK plus KD, but MD is equal to MG plus GD, so MG plus GD is less than MK plus KD, and if we subtract MG, which is equal to MK, from both sides, we find that GD is less than KD. Let's now prove that KD is less than LD. Noticing that we have two triangles, such that MK is equal to ML, and they both share MD, notice that angle LMD is greater than angle KMD. So we know that LD will be greater than KD, because it corresponds to a greater angle. We can similarly prove that HD is greater than LD. This proves the second part of the proposition. Let's now prove the third part. We will first draw DA such that it passes through the center of the circle, and let's also draw DH. Now Euclid uses DK, but so that we have more room, we'll use H. What we want to show is that there's only one other point on the circumference, such that the distance from that point to D is equal to DH, and that point will be on the other side of DA. Now we know this point will be on the other side of DA because if it was on the same side of DA as DH, and if it was on this side of DH, then the line connecting that point and D will be shorter than DH, as we have proved. And if it is on the other side of DH, then the line connecting that point and D will be longer than DH, as we've proved. To prove that such a point exists, draw MB such that angle DMB is equal to angle DMH. Now noticing that we have two triangles that share MD, that have two angles equal, and that MH is equal to MB, being radii of the same circle, these two triangles are therefore equal and DH will equal DB. Now we know this point is unique because if we pick another point that is on this side of DB, the line from D to that point will be shorter, as we've already proved. And if we pick a point on the other side of DB, then the line from D to that point will be longer than DB, as we have already proved.